Hello, welcome to this video. I'm going to show you how to undertake the RVE modeling of a meta-matrix composite, and this is going to be based on the composite having ellipsoidal particles. So let's sit back and relax as we get started with this modeling. Welcome to CM Videos, which is a YouTube channel where we try to help you get started with modeling. And if you're already down the modeling route, we try to also help you curate the best solutions, effective solutions for your FEA problem. So the first thing we need to say here is that this is a micrograph taken from this publication by Pandiyarajan. And it shows essentially, if you look very closely here, the particles, sometimes they have different shapes in them. And particle shapes for meta-matrix composites can be spherical, ellipsoidal, plate-like, cylindrical, or irregular. And we've done a previous video which I put on the cards focusing on spherical shape. This one we're looking at an ellipsoidal shape, and I'm going to demonstrate how you can do this. So the domain we're going to be using is basically a domain that looks like this. It's got dimensions, length, width, and height as given, and the material will be a reinforced particle reinforced meta-matrix composite where the reinforcement is silicon carbide with properties given. And I'd like you to note the volume fraction here is 5%, and the aluminium is the matrix made of this, and I've allowed this aluminium to have a post-yield strain softening. Now the next thing to say is that the silica has an ellipsoidal shape, as against the previous video that I made where the shape was spherical. And in order to use the Monte Carlo approach, I've assumed that this spherical shapes, ellipsoidal shape, is circumscribed within a sphere with a given diameter of so. So if you imagine this as our structure, so this is ellipsoidal particles is circumscribed within the system here. So I need you to know the dimensions, the length, the diameter of the fiber of the sphere is D, and the major axis of the ellipse, semi-major axis of the ellipse is A, semi-minor axis B and C, and these are the dimensions. Of course, the question to say is how many ellipsoidal particles are we interested in this RVE that we're using? How much ellipsoidal particles will fit into it? And I'll do a simple calculation to show you that. So this is a typical representation of the RVE, with particles already distributed in the ellipsoidal shape. So we know the length, the width, and the height. Each particle has a major axis of 2 times A, which is a semi-minor major axis of it will be A. So there is the other direction, which is 2B, and the y direction, which is 2C. So if we use that, the volume of an ellipse is 4 over 3 pi ABC. Okay, so we'll use it divided by the volume of the structure here. So if you do some rearranging, you end up with this relationship. So for our case here, we're working with a 5% volume fraction, which is this. The diameter of the circle in which it is being circumscribed is 40. So if I take 50% of that, I get 20 microns. 25% of that, I get that. So this is basically how I'm trying to make a decision on the shape of the ellipsoid that we're using. And of course, the length, width, and height is 120 micron. If you do the calculation, it works out that you should have about 10 ellipsoidal particles to capture this 5% volume fraction within this RVE window. So that's what we're using. And then I'll use my Monte Carlo system to generate this random representation within MATLAB of what the particles would be. So first thing is that they are randomly positioned and they are oriented along this x-axis. Of course, you could change it orienting in a different direction, but this is what I'm working with. So I'll note the positions of this ellipsoid, especially the center line, the center of this ellipsoid. So we're going to be using this in creating our model. Okay, now the two case studies that we'll be looking at will be one, a tensile deformation, and a shear deformation on the XZ plane. So okay, so here we are in ABAQUS. So there are two ways that I'm going to do this. I'm going to show you a physical, manual way of creating the domain, and then I also show you how you can do this using a script that I'll provide. So let's do the first quick, easy, manual way of doing that. So if we double click here, we'll start first by creating the part. So let's start with the matrix. The matrix is easy to create. So okay, so what will be the dimensions of the matrix? So I'll click 0, 0. 120, 120. So that gives me the dimensions, and then I will extrude that to create another 120. So this will be the matrix. So this is fine. This is not a particularly difficult thing to do. So to create the ellipse, we're going to have to do this differently. So let's look at the ellipse. Okay, ellipsoid. So we call that ellipsoid. It's going to be revolved. So what I'm going to do here is I'm going to create a new construction line because I want my x-axis to be the axis of interest, okay, rather than the y-axis. So then we could do this. Okay, I'll click here. So this point will be 20 on the x-axis and 0. Okay, and the y-axis could be 10, 0 and 10. Okay, so then I need to close it up from here to there, right? And I need to also delete. So let me trim off the part at the top. So we've got our structure this way. Okay, so now done. So it says select the construction line you want to use as your act as your center line. So I want to revolve about this x-axis, and then I put 360. So that revolves, and then we have the kind of shape that we're interested in, okay, which is the ellipsoid. So that's fantastic. So now let's go to the assembly. Under our assembly, if you double click on the assembly, so you got the ellipsoid and the particles, they are both already there. Okay, so we're not having to move this to different locations on the model. But what I'm going to do, let me just create as many patterns of that as possible. So okay, so that it will be easy just to move things in the way we want. So if I take out that, so why not let me orient about this x-axis and then flip it around. Okay, right, so this is kind of what we have. So we could create multiple numbers. Yeah, so that's probably about enough. So we've got enough of that, and then we could remove that, those two. Okay, so we've got that in place, and then the next thing we need to do is just click to translate them. First thing, like we did before, so I'll pick up this first one. The center line is the point of interest, 69, 81, 89, 69, 81, 89 is, so that moves into that location. Okay, so maybe we can even switch this into a surface mode so we could see. So that moves into that position. So the next one, we pick on that. The center line is, so pick on that, done. So that's the center, 70, 30, 80, 70, 30, 80. Excellent. So we're going to then quickly run through to the end. Okay, so we've done all that, so we'll move them into their positions. So the next thing we need to then do now is to basically to merge cut them. So we select all of them, select, and let's call that our MMC merged. Okay, so return the boundaries, select everything at once. Okay, so that merges it, and then if we go back to the path module, so within the path module you see MMC merged. So this gives you the result, part of it of how it's going to look. Okay, so this is one way that we can do this. Okay, so I'm going to one method, so let's call this one method. So let's create a second model method. So this is another way that I'll prefer to use it instead of using it in this kind of laborious way. So let's use a script. So let me show you the script that we're going to use for this. So here is a script that I've written that can do the same. So I'll provide this script as a link in the description section of this video. So please, let's use this. So I'll copy that. So I'll go into my model. Okay, go to this point and paste the script. So clearly what the script will do is that it will just do exactly what we've done before, regenerate the model, and then you get it. So it's a more comprehensive version. It translates all the particles into the position that they should be, and this is fine. Okay, so we've got that. So and we're going to work with the script, and then it creates the materials and all that. So within the composite section, so we're going to Extrude-cut to trim off all the boundary fibers. So you select there and select here, click on there. Okay, so we'll do this, create a big one, done. Extrude-cut all through, so it trims off that fiber. So we'll do that for the remaining. we'll just check. Okay, so if there are still some remaining fibers in your case, please go ahead and try whatever until you get it all looking correct. So we trimmed up all the boundary fibers. So let's just then make sure that our section assignment is correct. So the metrics, right? So what I'm going to do is I'm going to select to remove only by cells the metrics. So leaving only the fiber. So the inclusion, I double click here to pick all the fibers, not all the inclusions. So that's fine. The metrics, so how do we do the metrics? We invert the selection, leaving only the metrics. So they'll select that. Okay, so we replace everything and then I change to my material default, so it does show me everything is correctly selected. So we can then mesh. So the meshing is recommending a 6, so we accept that. I'll try to, because of the complex architecture, we'll use a tetrahedron. If you're not going to use a tetrahedron, then you have to, do partitioning of the model until you get it to work. But tetrahedron will be the easier, quicker option. So this is our mesh. It's an acceptable mesh for this kind of simulation. So the other things we need to do is we need to create the set of all the boundaries. So if you turn this off, so let's just create the set. So X back, just the X back alone. So this is the X axis at the back of it. So I need to select all that. Okay, so that's fine. So we'll do that for the remaining. Okay, so we have selected all the created sets. So X back, X front, Y base, Y top, Z back, Z front. So that's all perfectly selected. So what we then need to do is within our assembly module. So I like to know what this corner here is. So point, find the position of this corner. So it's giving us as 120, 0, 120. So let's create a reference point. Okay, so within the assembly module to reference point, so let's make it at 130, 0, 120. So that will just be a reference point there. So still within the assembly module, so let's create a set which I'm calling LP set. All right, so that's just done. Now, so the remaining things, so we've gone the set. So let's create a step. Okay, so some constraints. So I'm going to call this my X constraint. So I'm using a star equation to do this. So what we want to do here, this is the set. I'm constraining the front in 1 degree of freedom minus 1, constraining it with respect to the reference point in 1 degree of freedom. So these two are connected. So I could then apply my X-tensile load, X-tensile extension. Okay, displacement boundary condition, and I'm going to assign that to my reference point and in the X direction. So maybe 12 should be fine. So we have that and 12. Okay, now the other things is the boundary conditions we need. So X back would have a roller support. So the back in a roller support in the one direction. Y base will also have a roller support in the 2 direction, and Z back will also have a roller support, and that would also be in the 3rd direction. So we've got all that, so we can create a job MMC ellipsoid, so we can work with this. All right, so we can submit that to run, so that just start running. So what we're going to then do is, all right, so I'm going to copy and create a model of this, which I'm going to call MMCs ellipsoid shear. Okay, so we are going to use the same model, but we're going to work with shear. So with shear case, so think about what's happening here. So the back we need to fix completely. Okay, so I'm fixing the back completely. My extents, because we are doing YZ shear, will not be in the 2 direction, it will actually be in the 3 direction. So maybe let's do that 20. Okay, so we're shearing in that face. The Y base will have to be suppressed, Z back will have to be suppressed. So we need the X front, so X front roller. Okay, so we link it to the front, and we're only constraining it in the 1 and 2 direction because we want it to be free to roll in the 3 direction. So I change this, so this becomes XY shear, so that's fine. So we'll create that job again, MMC shear. Okay, so we could submit that to run as well. So it's done. So both jobs are running, so wait for it to run and then we'll look at the results. Okay, so let's look at the results. So the tensile case has finished. So if we look at the results of the tensile case, okay, so we've got some results, some interesting result that looks like this. So this is the shear case, the X-tensile case. So it gives us a simulation. So I always like to show the plastic strain value. So it gives you some interesting result of what is happening here. Okay, so how the system is basically deforming in the X direction, and you could see the positions of the particles, how they are adapting in their cases. So we could look at the the average stress, the average plastic strain, and the minimum plastic strain. These are all the values that we have here. So this is the version that we would probably use here. So it shows the different stages in the formation of this body as it starts from beginning, then go gradually until we get to the end. So you see different deformations. So around where the particles are, there's a lot of plastic deformation holding the particle in place, and generally. So this is what you see in tension in this X direction extension. So if we look at the ellipsoidal shear case, so if we monitor the result, is still running, so it's somewhere around 33% complete. So let's just have a quick look at the result. So for the shear case, so you get a similar situation, XZ. So X in the Z direction is what we're seeing. So the system, so if we go back to the original position, okay, so this is the XZ phase, so it's shearing in this direction. Okay, so we could look at the plastic strain as well, and you get some again an interesting result like what we've been doing, what we're showing. So this is a sort of result that you can get when you have particles. So you could see what's happening here. The particles here is quite strong in a rigid position, not allowing movement. Generally, this is a sort of result that you will expect to get when you're trying to do an ellipsoidal case using a particulate composite. So that's really all that I wanted to show in this video, and I hope that you found it useful. Again, if this is the kind of content that you like, please do subscribe to this channel. And for those that already subscribed and that keep coming back to these videos, I really appreciate you, and I hope you keep suggesting videos that you would like me to make, and I'll review them and make them. So thank you, and see you in the next video. Bye bye.